Welcome back, everyone. Today, we're diving into paper 24 of the Non-Holomorphic Bird Map series, and this one reads like a proper detective story. It's all about a single critical failure from paper 23 that just refused to make sense. We've got a powerful new tool, a set of crucial tests, and one result that was just wrong. Okay, so let's set the scene. Paper 23 introduced a brand new analysis tool, the Conformal Padé Borel engine. Now, its whole job was to be an independent check, a second opinion on all the findings from papers 19 to 22 about the structure of the bird map. So meet our protagonist, this new engine. At its heart, it uses a conformal map, specifically this phi of s equals s over 1 plus s over sc, to basically remap the entire problem. The goal was simple. Look at the whole Feigenbaum Atlas through this new mathematical lens and see if the old conclusions still stood. And this table? This is where our mystery begins. Look, before you can trust any new tool, you have to calibrate it. That's what the G4 Planet Pulse self-test is for. You basically plant a fake singularity in the data and see if your engine can find it. As you can see, it was brilliant. It passed with machine precision on 5 out of the 6 ladders. But then, look at that last one. On the Class C Orbit Multiplier, a crucial observable, it failed. The engine was completely blind to a target it was designed to see. So the question is, why? Well, the investigation in paper 24 started right where any good detective would, with the evidence, the data itself. I mean, if the tool is sound, maybe the input was just garbage, right? What was so different about the data for this one particular ladder? And right away, a huge clue. It turns out that every single previous test on this failing ladder had used surrogate coefficients. They weren't the true Taylor coefficients, they were just estimates from finite different samples. And that means they could be full of numerical artifacts. So, first order of business for paper 24, get the real coefficients and rule out contaminated data once and for all. And they were not messing around. Paper 24 goes into detail on how they built a whole new generator just for this. It uses a Newton cascade to nail down the orbit points, then differentiates the fixed point equations to get the coefficients recursively. And get this, they calculated everything out to n equals 80 with a staggering 120 digits of precision. This data was pristine, unimpeachable. Okay, so we've got our brand new ultra-high precision data. The team reruns the test, and the expectation is pretty clear, right? The G4 self-test is going to pass, the mystery is solved, and the bad data is our culprit. Case closed. But that is not what happened. It failed. Again, even with the perfect data. For every order tested, n equals 40, 60, and 80, and for every single Padé degree they tried, the systems were either singular or just totally blind to the pole. This was the big twist. The data was innocent. The problem had to be something much, much deeper. So think about it. If the tool's design is generally solid, and we know the data is now perfect, the problem has to be fundamental. It has to be some kind of structural property of the specific observable that just makes it incompatible with this tool. The hunt for the smoking gun was on. And here it is. The clue was hiding in plain sight, in the coefficients themselves, their intrinsic geometric growth rate, what the paper calls R true. You see, for the 5 ladders where the test passed, that rate was hanging out around 2.0. But for our failing ladder, it was dramatically slower, barely above 1.1. The entire mystery comes down to this one number, 1.0952. That's the precise growth rate that cracks the case. This slow growth is the smoking gun. But how? How does a slightly slower growth rate cause a sophisticated analysis engine to just completely fall apart? The answer is all about that conformal map. A slow growth rate like this has a wild consequence. It squishes all the important analytical information into an incredibly narrow window in the transformed variable, a tiny width of just 0.044. And when your space is that compressed, the numerical basis for your Padé approximates becomes almost singular. They just don't have enough resolution to tell the signal from the noise. The tool, for all intents and purposes, goes blind. Now, to be absolutely sure this wasn't just some unlucky parameter choice, paper 24 ran one last check. They recentered the map right on the Feigenbaum target itself, setting SC equal to SF. This should have made the engine more sensitive, if anything. And the result? Another failure. This was the final nail in the coffin. The limitation was absolutely structural, not just a matter of tuning. And that brings us to the formal verdict of paper 24. This conformal engine has what the author calls a resolution ceiling. for this one specific observable. It's not a bug, it's not an error, it is a provable structural limit. At the orders we can access, the tools simply cannot resolve this particular signal. So here's the big question. Does this one failure invalidate the entire project? Does it mean the conclusion about Feigenbaum singularities is wrong? Not at all. And this is where having a combined atlas using multiple independent tools really pays off. This table really ties it all together. Let's focus on our problem observable. We see the conformal engine fails its self-test, sure. But look at the original Gamma family engine from papers 19 through 22. On this exact same ladder, it passes its own calibration test. And here's the most important part. Both engines, independently, return a Feigenbaum negative verdict on the real data. You see, the two different analysis engines perfectly cover each other's blind spots. Where one tool hits its resolution ceiling, the other one sees everything clearly. And that overlap makes the final conclusion that there are no Feigenbaum singularities in the non-holomorphic bird map incredibly robust. The atlas is doubly confirmed. Case closed. And this brings us to the real takeaway from paper 2.4. This whole detective story wasn't really about a failure. It was about meticulously mapping the boundaries of a powerful analytical tool. Because the best science doesn't just come from finding signals, it comes from deeply understanding the blind spots in our methods. As the paper puts it perfectly, understanding where one tool's power ends is the first step to inventing the next one.